Right, if you still remember, in the previous chapter, we already cover part of gas diffusion, where in the under gas diffusion part, we learn how can we measure the flux, which is depends on the types of mechanism occur, whether it is equimolar or A diffusing through non-diffusing stagnant B. Then after that, we learn about the diffusion coefficient, the DAB. Well, in this chapter, it is also arranged in a similar pattern, in which that we also learn what types of mechanism happen in liquid diffusion and how can we calculate the diffusion coefficient for liquid. Okay. Alright, this is the content outline that we will cover for today's session. And the first part, which is about equimolar counter diffusion in liquid, which is it is part of the mechanism occur in liquid diffusion. And the second part, which is about diffusion of A through stagnant and non-diffusing B. So if you can remember that these two mechanisms, we already learned it before in gas diffusion. But today, it is just focused for liquid diffusion instead of gas diffusion. And lastly, we will cover on the prediction of diffusivity for liquid diffusion, the DAB, in terms of liquid diffusion. Okay, for equimolar counter diffusion in liquid, the mechanism is the same as what happened in gas diffusion, in which that the movement or the flux can be occur in both direction. Alright, and this is the general formula for equimolar counter diffusion in liquid. If you still remember, this is actually the general term for mass transfer. Okay, it happens due to the difference in concentration. So when it's being rewrite the equation for liquid diffusion, the term is slightly changed. If you can notice that we have new terms here, which is CAV, which is concentration average, and XA1 minus XA2 here, which is the mass fraction at 0.1 and 0.2. And Z2 minus Z1 still means the same thing, which is the distance between 0.1 and 0.2. And lastly, we still have the DAB here, which is means that the coefficient diffusion. Okay, and here is the formula to calculate the C average. C average basically the meanings of the ratio. It means that the ratio between rho, which is the density over molecular weight in average at two different points. Okay, if you can see that this is the rho over molecular weight at 0.1, and the second terms here is basically the ratio between density over molecular weight at 0.2. Okay, so we got this average concentration through this formula. And for this one is actually the formula to calculate the XA1 and XA2. For XA2, you just change the term here into, instead of A1, it will change to A2 for XA2. Okay, So basically it refers to the mass fraction at point 1 and point 2. Okay, and this is the molecular weight at point 1, okay, according to this formula. So total weight of solution, usually it depends on the question. Sometimes if it's given, then you can use the information from the question, but if it's not given, and you can use through assumption, okay, like 100 kg or 1000 kg, something like that. Okay, okay, the next part which is diffusion of A through stagnant non-diffusing B. Still the same, in which that in this condition only one solute, which is solute A, diffuse through non-diffusing B, where B cannot diffuse through A. Still the same types of mechanism which is we learn in gas diffusion. So for this case, the equation is here, where we also have new additional parameters here. If you can see that we have the XBM terms here at the bottom. So what does it mean by XBM terms here? So XBM is actually can be derived through this equation. Okay, and again the C average, still we using the same method or same derivation that we use for equimolar counter diffusion, which is the ratio average between the density and the molecular weight. And same again for the mass fraction. So mass fraction here we have XA1, but however if we look at here, we might use this one a lot, sorry, XA1 and XA2. So this one is actually the derivation for XA1, but if you want to use the derivation for XA2, okay, basically this you also use the same formula, but you just change the concept according to the location or point of the location, where this one might be replaced with A2 if you want to find for XA2. Same goes to the bottom part here. Okay, and also this one. All right, so here we also have XB2 and XB1. Okay, so how can we obtain the XB2 and XB1? So once if you have the XA1 and XA2, you can directly get the XB1 and XB2. How? Which is XB1 is actually 1 minus XA1, and XB2 is 1 minus XA2. Okay, same goes to molecular weight, just use the same concept. Okay, let's start doing example for a diffusion of A through stagnant non-diffusing B. Okay, I give you few times to read the question, then after that we will extract the information from the question. Okay, so if you look at the question here, it shows that ethanol, which is considered as A, and water, which is considered as B, where in this case water is insoluble, which means that the non-diffusing here is B, which is water in this case, where it forms a stagnant film with the thickness of 2 meter. So here, which is refer to the distance Z2 minus Z1 at 293 Kelvin. Okay, so if is in the case of non-diffusing, so there's only Na available, so Nb is 0. Okay, so we actually want to find the Na because Nb is 0, it is non-diffusing B. At point 1, the concentration of ethanol is given here, 16.8 weight percent, with the density at point 1 is 972.8. And at point 2, the concentration of ethanol is 6.8 weight percent, and the density is 988.1. And the DAB, which is the diffusivity of ethanol, the coefficient, the DAB, is given here. And assume that the total weight of the solution is 100 kg. Calculate the Na. Okay, so what is the next step? Okay, first of all, you need to list down what is the input that we obtain from the question. So according to the question, we know that the solute A is ethanol and solution B is water with the distance 2 millimeter and the temperature is 293. Okay, so here is the important part that you have to list down and put it carefully, especially related to the concentration. So we have 2 point, point 1 and point 2. So concentration of A at point 1 is 16.8 and concentration A at point 2 is 6.8, with the density at different point is listed here, 972 and 988.1. And the diffusivity coefficient is given, which is 7.4 to power of minus 10. And the next step is we need to do the mind mapping plan to solve the question. So if you still remember that the question asks us to determine the Na, which is the flux, the mass transfer for solute A. Okay, so from this formula, we have to complete we have to carefully check all the parameters which is involved in this equation in order to make sure all the parameters is able to be determined. Okay, so for example, in this case, we check one by one. Yeah, okay, so let's start with the first one, which is the DAB. So the DAB in this case is given, which is 7.4. C average, okay, it is not actually given directly, but we can calculate it through this formula, C average, which is here. Okay, where we need the density at 2 different points. Yes, we do have it, point 1 and point 2, and the molecular weight at point 1 and molecular weight at point 2, and it's the same as well. These two terms can be obtained from this formula. Okay, and the XBM term, which is here, where we need the concentration for B2 and xb1. Okay, yes, we can get it as well. If you still remember in the previous slide, I explained already how can we determine the xb2 and xb1. Okay, and lastly the xa1 and xa2 here. Okay, so after we check all the parameters is possible to be calculated, then we proceed with the calculation step. Right, for the next step is we want to determine the parameters which is needed in the equation. But first of all, there are few important parameters that you need to determine first. Okay, for example, information such as the molecular weight of A and molecular weight of B is important. Okay, so for example, MA, which is the molecular weight of ethanol, and MB, molecular weight of water. Okay, so these two information sometimes is given in the equation, but if it's not given, you can get it from periodic table. Okay, and one more thing, the assumed total weight condition. Okay, in the question also sometimes is provided, and in this case is provided in the equation, which is total weight is 100 kg. If it's not given, you can just assume. Okay, and next step is mole fraction determination. Okay, mole fraction is xa1 and xa2. Okay, and we know that in the question it is given that the ca1 and ca2, the ca1 is 16.8 and ca2 is 9.8. so how about the cb1 and cb2? Okay, so we can determine the cb1 and cb2 by just making 100 minus with the ca1, then you get the cb1. Same goes to cb2, 100 minus with ca2, then you got the cb2. Now next step is we want to determine the xa1. Okay, this is our intention. So if you can see here, there's the reason why we need the information about the molecular weight. For example, we need the information about the molecular weight of A, and we also need information about the molecular weight of B. Okay, and here as well we need a molecular weight of A. Okay, so by using the information here and also information of the concentration at different point, we will manage to get the XA1 and XA and XB at different point. And we also can calculate the XBM as well. The formula for SBM is given in this equation, where we need information about SB2 and XB1, which is available here. Here is XB1 and this one is XB2. Okay, that's it. Okay, let's move to the next step, in which that in this step we need to calculate the molecular weight average at different point, which is point 1 and point 2. Okay, so here is the formula given to calculate the molecular weight average at point 1. Okay, so this is the formula to calculate the MW1, M1. Okay, so based on the equation here, the total weight solution is actually given in the equation, which is 100 kg. Okay, if you want to confirm about it, you can refer to the question where the information about the total weight solution is given as 100. In the case where the total weight is not given, you can make assumption. Okay, so how about the molecular weight average at point 2? Well, the same procedure that you have to use, but the only difference is for this formula is the bottom part here. So instead of using XA1 plus XB1, you have to change it into XA2 plus XB2, which is refer that the mole fraction at point 2 involving component A and component B. Okay, now let's move to the next step, where you need to determine the average concentration, the CAV. Okay, so again, here is the formula. So the row 1 and row 2 is provided in the question. Again, refer to the previous slide in the input slide. Okay, and the molecular weight average at point 1 and molecular weight average at point 2 is actually calculated from this step. This is M1 and the other one is actually M2. Then you manage to get the molecular weight. You manage to get the C average at 50.04. Okay. And finally, when you already calculate all the parameters needed in the equation here, you will manage to get the NA, the flux value of A. Okay, remember the DAB is given in the question. The CAV, the C average, is actually here in step 6. You just calculate it already. The XA1 and XA2. For this one, you need the information in step 4, where if you already have the CA1 and CA2, then you manage to get the difference between this value. Okay, and XBM, same goes to XBM. Okay, it's actually from this info. Okay, so refer back to the step 4. Okay, and lastly, the Z2 minus Z1 also provided in the question. Okay, then lastly, you get the value of flux, which is 8.95 to the power of 10 minus 7, with the unit is kg mole per meter square second. That's it. Okay, now we come to the part of prediction for diffusion coefficient, the DAB, for liquid diffusion. So basically, there are two methods can be used for the prediction of diffusivity in liquid. The first one is Stokes-Einstein equation, and the second one is Wilkie-Chang equation. Okay, here is the formula for Stokes-Einstein equation. I think there's not much complicated parameters here, where the mu here stand for viscosity of the solution, and VA is actually the solid molar volume, which is from table 632. Okay, and we go to the next step, which is the Wilkie-Chang equation. So for Wilkie-Chang equation is quite the same as well, but we have another two additional terms here, which is the sigma terms here and the MB. MB is actually stand for molecular weight of the solution. For example, if solute A diffuse into solute B, which is water, so the MB is actually molecular weight of the water. Okay, again, the mu here as well refers to the viscosity of the solid B, and VA is solid molar volume, where we can get it from table 632. Okay, but for this session or for diploma level, we just focus on the Wilkie-Chang method only. Okay, next I will explain in detail about the Wilkie-Chang equation, especially on how can we determine the parameters inside the equation. Okay, this is the equation. Okay, so let's start with one by one. Okay, first one is sigma. The sigma here is actually defined as association parameters. Okay, for example, if your solution B is water, then the value is 2.6. But if it is like ether, it's become 1. It's something like this. This is the only 6 of the component that we have for the solution B. Okay, and next one is molecular weight. Okay, so molecular weight, let's say our solution B is water, so molecular weight is 18.02. okay, in other cases, then you need to get the molecular weight from periodic table, or sometimes it's given in the question. And next one is the mu B, which is mu is referred to the viscosity of the solution B. In this case is water. This one you need to use the appendix for the table of viscosity of liquid water. Again, it depends on the condition of the liquid. Okay, for example, let's say the question refers that the diffusion occur at 25 degrees C, for example. Okay, so at 25 degrees C, the value of viscosity is 0.8937. Okay, it depends on the question and conditions stated in the question. Alright, next one is VA, which is defined as the atomic and molar volume. Okay, and this one is refer to the component. Be careful, this one is for solute A, it's not for solute B. So let's say we have solute A is ethanol, ETOH, I just simplify it, ETOH, okay, ethanol, and solute B is water, for example. So if you notice that for other parameters here, parameters 1, 2 and 3 is actually the properties or the parameters is obtained for solute B, which is water. Okay, but for VA, which is the diffuse liquid, the flux of A that we want to determine, so the VA here is actually the atomic and molar volume for the solute A, which is in this case is ethanol. Alright, okay, let's do example 2, which is related to the prediction of diffusivity, or what we call DAB in liquid diffusion. Alright, I give you a few minutes to read through the question. Okay, so have a look at the question here. The question asks you to predict the diffusion coefficient, or what we call as DAB, of acetone in water at temperature 25 degrees C and 50 degrees C by using Wilkie-Chang equation. So we know that here the liquid A, which is acetone, and liquid B is water. And you have to determine the DAB at two conditions. The first condition at 25 degrees C and the second condition at 50 degrees C. And the experimental value which is given, the experimental value, this one is actually referred to the DAB value which is obtained from the experimental work. Okay, but the question asks you to determine the DAB by using the Wilkie-Cheng. So once you get the DAB from Wilkie-Cheng, so that you can compare the value with the value from the experiment. Okay, and some other information also is given, such as molecular weight of B, solution B, which is water, at 18 kg over kg mole, and association parameter for water, which is at 2.6, and this one is actually the sigma from the Wilkie-Cheng equation. Okay, so therefore we know that the question asks you to determine the DAB at two conditions, 25 degrees C and 50 degrees C, by using Wilkie-Cheng equation. So here is the Wilkie-Cheng equation. Okay, so before you start to substitute all the value into the equation, it is very important for you to check one by one the information or the parameters involved in the equation is available or not. Okay, whether the value can be get from the equation or maybe from appendix given. Okay, let's start with the first one, which is the sigma or association parameter. In this case, the solution B is actually water, so the value of association parameter for water is 2.6, and this value is actually already given in the question. Okay, and the next one is molecular weight. For molecular weight of water, which is also given in the equation, which is 18.02, and viscosity. Okay, viscosity of liquid B. In this case, viscosity of water. And remember, this is also depends on temperature that you want to determine. Depends on the DAB at which temperature. For example, you want to determine the DAB at temperature 25 degrees C. So the viscosity of B here should be at 25 degrees C, where from this one, okay, from this table A to 4, at temperature 25 degrees C, the viscosity is actually 0.8937. Okay, but for example, you want to determine the DAB at temperature 50 degrees C, so the mu B is actually should be here, which is 0.5494. Okay, and next one is VA. Okay, so VA is actually referred to the atomic and molar volumes of liquid A, and in this case liquid A as acetone. Okay, so based on the previous slide before, where I show you how can we determine the VA, so use that method to get the VA for acetone. And last one is temperature. Okay, this one again, I said that if you want to get the DAB at 25 degrees C, then you have to use that temperature to be substituted here. If that is at 50, then it should be at 50 degrees C. But again, that one, of course, you need to convert the unit into Kelvin for this one. Okay. Okay, here I will explain in detail how can we solve the question. Okay, so first one is we should know what is the input from our question, and I also suggest you to do this kind of table to make things easy for you to understand the question better. Okay, so we know that the solution A in the question is actually acetone, and solution B is water, and the question also provide us the experimental DAV value, which is 1.28 to the power of 10 to the power of minus 9, and the stoichiometric equation for acetone is given. Then we will get information which is needed to be substituted in the equation. If you still remember in the previous slide, we need information such as molecular weight and association parameter. So for molecular weight of water, which is molecular weight of B, which is 18.06, and association parameter sigma is 2.6. And next one is we need to determine the mu B, which is the viscosity. Okay, and again this one I said before, it depends on at which temperature you want to determine for DAB. Okay, let's say you want to determine the DAB at temperature 25 degrees C, so viscosity value of B that you need to determine is actually at this temperature 25. Okay, which is given here, and if it's at 25 degrees C, and here is the viscosity value, and here I show you how can we get the value of viscosity. So at 25 is actually given here. Okay, and also same also as at 50 degrees C, which is here. Okay, next step is we need to get the VA value, which is the atomic molar volume, and as we know that we need this table 632 to get this value. Okay, so the solution A in this case is acetone, and the formula is given here. So how can we determine the VA value? Okay, right, so based on the formula here, we know that acetone consists of C, carbon, hydrogen and oxygen, and it has 3C, 6H and 1O, and the value for the value of VA for each types of the atom here is provided in this table. For example, the value for C is 14.8, H 3.7 and O is 7.4. Okay, so the total value for each atom, you can just multiply between the quantity here with the VA, then you get the total value for carbon, hydrogen and oxygen, and this is the total value for VA, which is the VA value that we need to be used in this equation. Okay, lastly, since all the value or parameters needed in equation is already determined, so we just need to substitute into the equation. Okay, so here is the Wilkinson equation that we need to use to substitute all the information that we already calculated or we already got it from the tables. Okay, so since we already have the sigma, mu B, T, mu B and VA, so just substitute into the equation. Okay, if you notice here, I divide the terms into two parts, and I just calculate using Excel, but for you, of course, you have to use calculator. Okay, so I just separate it into different terms. Yeah? Like this one is the terms 1 and this one is terms 2. Okay, so I calculate one by one of this term. Like this one is terms alpha, and this one is beta, and DAB is actually 1.173 times with beta and alpha, where I calculate it using Excel. Then finally I get the value here. Okay, but for you, of course, you can just simply use your calculator. Okay, but it's actually good for you to just, you know, break the parts in the equation to a smaller part, so that it will easy for you to do check and balance at the end. Okay, but at the end it's up to you which one is easier for you to substitute the value and get the DAB at the end. Okay, so same goes to the part for if you want to calculate the DAB at 50 degrees C. Okay, the only difference is the temperature that you substitute here, and of course the value of mu B here that you use here. Of course, you use the mu B at temperature 50 degrees C instead of 25 degrees C. Okay, and remember that the temperature here, you should use temperature in Kelvin, not in Celsius, so you have to do some unit conversion. Okay, that's it. Alright, lastly, we can do comparison between the value which is we calculate from the Wilkie-Chang equation and the value of DAB which is given from experimental value. And remember that the DAB value which is given in the equation, which is only at 25 degrees C. So that's why our comparison with the Wilkie-Chang value is only involve the value that we calculate at temperature 25 degrees C only. So from the comparison here, okay, we can say that the value more or less the same. Okay, even though we calculated using Wilkie-Chang equation, and it has not much different with the value obtained from the experiment. Okay, the end. I hope you understand the lesson. If you have any question, we can furtherly discuss during the forum session. See you again. Bye.